I'm Riya Ponraj, a PhD candidate from the University of Oregon. First, I would like to thank the organizers to give me this opportunity to present here. And I'm truly grateful for the Internet Society for selecting me as one of the Pulse Research Fellows. So let's get started with my work today, which is like how we can map the network layer to the physical layer, which is helpful for the enhanced internet resilience and the security. And we are going to deal with this using the submarine cables and the trace route traverses through them. So, to begin with, let's start with an example. Let's say you send a message to your friend who is in another country. How does that message actually gets there? We might think it's because of the wireless, but more than that, over 99% of the internet traffic, international traffic, is carried by the submarine cable. And so, in that kind of situation, when a cable is cut or it's congested or if it is disrupted by some natural disaster, it is going to affect the services that is making use of that cable to send the traffic. So it could be the banking services, cloud services, education, and various services. In addition to that, we have the lack of visibility here. Like, we cannot exactly say which cables the particular traffic depends on. There is no transparency or data driven visibility here. And even in few cases, operators might not publish the accurate physical to logical layer information, which allows us to make more meaningful decisions about the resilience. So that led us to this motivation, like how we can map the logical layer to the physical layer, which gives us more information on how we can prevent all those issues that we've talked about earlier. So on the left, we are seeing the trace routes, which is a tool that allows us to see how packets move across the internet every day. And on the right, we are seeing the submarine cable map, which is like the actual fiber pathways under the ocean. But like we said before, there's no clear link between them. And this is why we need to map the logical layer to the physical layer. And why does it matter? Because if there's an outage or failures, we have to see where exactly the issue is and we have to rectify that issue faster. So if we could able to map the logical to physical layer, we can able to figure out which cables it is taking. And we could also improve the performance and the reliability of the traffic that are sent if we know the cable that we are using. So the goal here is to build a principled approach of mapping the trace routes to the submarine cables that is going to be beyond the heuristic approaches. And yes, of course, there are existing approaches like Intertubes, IGDB, Nautilus, and Calypso, but they're all based on heuristics and they do not generalize to the real world complexity. If there are any issues with MPLS tunnels or there are noisy IP data, the heuristics will not be helpful in those kind of scenarios. And other than these approaches, there are services like IP geolocation services. There are like hundreds of commercial services available online, and many of them can actually provide the reasonable state level information. But if it comes to a city level information, which is like exactly where the landing stations are, to say which cable it belongs to, the data becomes more inconsistent or unreliable in that kind of situation. And we have operator maps. Even though there are few maps available online, they're like not all of them are publicly available and not all of them are complete and updated regularly. So even though operators know the physical infrastructure, that rarely reaches the measurement community. So our approach here is how we can deal with it. Before that, why mapping the physical layer to logical layer is hard. So we have trace routes, which gives us IP addresses, RTT pattern, hop number. But what it doesn't give is like which cable it exactly takes, which landing stations are used, and when the path will change if there is a failure. And this is because we could able to infer it from the trace route, but the trace route cannot explicitly give that kind of information. So we need to come up with a method that learns purely from the structure of the data. And in this case, it's going to be the RTT from the structure of trace route. But the question here is, Can we really learn submarine cable fingerprints directly from the RTT patterns? And the answer is yes, we could able to do that. So the ocean crossings, like from one continent to the another continent, will show the different RTT spikes. If we see the image in the bottom, we can see the spikes. So the image in the bottom is like hundreds of trace routes going from the same source to the destination. So we can see in the beginning there is like around 1 millisecond to 7 millisecond, and we can see the spike which is going super high, and that is going to be a submarine cable. So from the trace route using the RDT patterns, we can say where the submarine cable crossings are, and our learning model can pick up these patterns on its own. So that's going to be the approach that we are going to use here. And how we are going to do is we are going to do that without using any labels, because there is no data source available online that says this particular trace route using this cable. So using label will not be that much helpful. Like even if we infer it from geolocation and everything, it is going to be not that much accurate. So we are going to use the self-supervised approach, like without using any labels. And we are going to learn the representations of the paths based on the RTT behavior across hops. And when we do this, paths crossing the same cable naturally cluster together, and the different cables will be separated on their own. And we could also see the corridor level structure, like if the trace routes are going from Asia to Europe or USA to Europe, we can see the differences in the RTT pattern representations. And these representation will be learned as the embeddings, and this allows us to generalize across different regions and new incoming data set as well. So the insights from this information is each cable is going to have the unique RTT pattern. So the model can learn directly from it. If we look on the right, we have two cables, which is going from Japan to USA. And the first cable is TGN Pacific, and the second cable is TPE. And if we use our model, it allows us to cluster them separately. And this gives us like the accuracy of around 78 to 80 percentage. So the thing here is like the same cable will have similar RTT signature. And if the model could learn the representation, it will cluster all the trace routes together. And if they are from different cables, they will have the different representations, and the clusters will be like separator. And that's what happening here. And the shifts in the cluster corresponded to the outages will allow us to say if there are any events that is causing the difference in the shifts in the clusters. And how and why it does matter for resilience and security. So if we could able to say the traffic is using this cable, we can say which international routes are really important for the particular country. And second, we could detect the single points of failure. So if a country or region depends only on one cable, even a small disruption can have a nationwide impact. So this is really helpful there. And the third thing is like it allows us to understand the impact of cable outages like in real time. So if there is a shift in the clusters in our embeddings, we can observe like there might be a congestion or something is happening, some event is happening, which is causing the shift in the clusters. And fourth, this insight improves the preparedness for natural disasters or any geopolitical risk like earthquakes or anything that might affect the cable. In that way, we can able to reroute our traffic using different cable. And finally, we could able to detect the suspicious rerouting or anomalies. Like this level of visibility allows us to see where traffic suddenly starts taking unexpected paths or insecure paths. And our next step is going to be like we are currently working on expanding it to more cables. Like right now, we have the resource for the two cables, and we are expanding it to three, four, and more cables. And we are modeling it for different corridors. Like it could be from US East to Europe, US West to Japan, inter African connections. And we're also analyzing the different types of cables. Like some cables could be parallel, which are next to each other, and some cables could be isolated, and there are like trunk and branch kind of cables. And finally, we are planning to collaborate with the operators to do the validation validation of our results. So to end, this approach allows us to show that submarine cable can be inferred even without labels. And this provides us the transparency between the physical layer dependencies. And finally, it allows us to demonstrate that we could able to learn from the structure of the dataset that we have. So yeah, thank you very much. If you have any questions, please let me know. Thank you.
Thank you, Riya. All right, we have some questions from the audience.
Okay.
Thank you for the very nice presentation and very cool work. I was wondering that eventually you want to try this on the wild. And I was wondering if situations like remote peering could look like a cable without being a cable, or could look like a cable that is elongated because, I don't know, maybe it's crossing the Atlantic, but it's starting somewhere in the middle of Europe. And an idea for further validation is that you could use, because there is a lot of trace route data archived historically, you could use natural experiments like the appearance of a new cable or the disruption of a cable because of an accident or because of an earthquake or something like that, to see if the cable that you had inferred suddenly cannot be inferred anymore. Thank you.
Yeah, thank you. Yeah, that's another part of our validation. We've thought about that, but thank you for your suggestion. We will work on that.
Great work. This problem is super relevant and at the same time super challenging. So my question is, if you use a latency-based approach to infer, can you detect outages or like cables in the Baltic Sea, for example, or between China and Taiwan? Because those cables are quite short, right? And you may not see the spike that you expect to see. And these cables are super important.
Exactly. There are like so many cables, but we're starting with the big cables and see how the results are coming along. But we will work on that too. Yeah, thank you.
Hi, Timur Friedman from Sorbonne University. Makes me nostalgic for my time at Deschutes Hall. I'm curious about satellite connections.
Right now, we're focused only with the cables. Yeah.
But if I might, why isn't the system, if you're looking for high RTT differences and it's unsupervised, do you think you might be picking up satellite connections?
That's a good question, but we haven't explored to that part yet, but we will have a look at it soon.
Yeah, Alex Kimmer from UC Davis. I'm Riya's mentor on the program. I think it's a good question about satellite kind of interference in the inference. I think it's pretty unlikely just because of the fraction of international traffic that actually crosses satellite links is quite low. In some regions, especially inland, that's different. Like in Central Africa, some interdomain links are satellite, but not in the use cases that Riya has been working with. But yeah, good question.
Thank you, Alex.
Hi, thank you for your talk. Just something for my clarification. So if like in a trace route, we see the last hop router and then a huge RTT difference, and then we see the next router, you're saying that doesn't really explain that it has traveled through a submarine cable. Could the large RTT difference be due to something else? Like just manually looking at trace route data?
Yeah, it could be due to something else, but how we are exactly predicting the submarine cable hops is like, we take the difference between the hops. So like you said, if you see the high RTT in one router, it might not be consistent in the entire trace route when we are taking the differences. It will be only in the hop where the submarine cable actually takes place. So in that way, we could able to extract only the submarine hop from that place.
So would you be able to extract the last hop? Like this is the last router that traffic passes before it goes through the submarine cable. Is that possible through your data?
Do you mean the last hop, the terrestrial hop that has taken place? Oh yeah, we can. We have the IP information, but we have the threshold. Like we take the submarine cable's length as the threshold and we do the speed of light. So if it is less than the threshold, we will eliminate those kind of results. And if it's greater than the threshold, we will keep them as the submarine cable hops.
Okay, thank you.
Thank you. One down there. Yep. Final question.
Hello, Antonia Fido from University of Twente. Thank you for a really nice presentation. So I was wondering, because I saw like in your last slide, as you also said, next steps would be like to also check for more cables or for different types of cables. And I was wondering if you have already thought like how, or if you need to change your approach in order to include this analysis.
Do you mean like how do we extend to more cables?
Yeah, because for example, also the previous question was like if you consider shorter cables. So if you consider different types of cables, or if you want to include more cables, so do you think that you need to change something, your methodology, or do you think that your approach is scalable so you can adapt to different
it is
scenarios?
scalable. The model is like the exactly same thing, but the input that we're going to give is like scalable. We can extend it to like how many cables that we want.
Okay. Okay. Thank you.
Yeah. All right. Go on.
So great research, by the way. Thank you for sharing it. I'm just curious how you see or how you determine if that is all the undersea cables that a provider has, because we may have up to 5 or 6 undersea cables. And how do you see all of them if we're just routing your one network to one cable?
Right now, we are not considering like all the 506 cable. We're considering like only 35 cables. We'll scale it to like more than 35 after we have better results for the 35 cables.
Okay.
This is Amrish. Part of this work, what we want to do is also some validation with operators, because I think it's important to have like actual data from operators. So there are cables, for example, coming from Cameroon to Latin America or from Angola to Latin America, where you might not get confusion because there's only one cable. And if we know the operators there and they can actually send us the latency, we can actually validate that information that we are getting and make sure that the clustering we are using is actually accurate.
Romain Fontaine from IHF. I just wanted to understand how confident are you as you scale. I think as you look at more and more cables, I think there's a lot of layers between IP and the physical one. Operators are, when you get capacity on a cable, it's not just on the cable, like they will give you from a colocation facility to another colocation facility. So there's that part that you don't see where the landing points are. But if I'm an operator in Tokyo and I get access to a cable, I'm probably gonna get access like from Tokyo, the landing point in somewhere on the beach, and then goes to US. So it, I think, get like very hard when you go through all the cables. I'm just wondering like how you're gonna proceed. Do you think it's at the end it's more an index that will tell you how likely you are to take a cable, or are you very confident that you're gonna nail all those cables or not?
Yeah. So currently we're working on that. So when I just included all the cables all together, the performance degraded, like you mentioned. So what we did is we did it like corridor wise, like we took cables that belong to US East to the Europe corridor as a set of cables and another set of cables. So we have like different corridors, and that will prevent the mismatch or the results.
Then I think your resiliency analysis is like trying to find how many cables there is in those corridors, right? Mm-hmm. There's a lot of redundancies. Okay, cool. Yeah. Thanks.
Yeah. I'm Marcelo from the University of Chile. And countries that have a dot shape, in the case of ours, we're a very long and thin country, so redundancy doesn't come natural for our geography. So we had this problem in the past 10 years ago that our logical network would say something, and then we would only get one cut of fiber and everything would go to hell, all the country or many regions at the same time. So it's extremely important what they are doing. So we will definitely link after this to see if we can put this research to try it out in our country. We really didn't. So congratulations.
But thank you very much, Riya. Appreciate you being up early.
Thank you very much. Also, you can reach out using my email. I posted it. Thank you very much.
Cool.